My dear friends, today I am going to derive a relation of magnetic field at a point due to infinite straight conductor. But before going to infinite straight conductor, first of all, I am having a conductor of finite length, and that conductor is, let it is from x to y. This is the length of my conductor through which some current is flowing, and let current flowing is equals to I. Okay. I consider a very small current element I mean to say current into length, that I'm talking about current element I mean to say I into dl. IDL is the current element and it is a vector quantity. You know very well, current is scalar. Current is scalar, but current element is a vector quantity. Okay, and its direction along which the current is flowing. Now, what's the problem? The problem is we know the current makes a magnetic field. Okay. Now, let the observation point is this observation point. This is the observation point, and I'm interested for finding what is the magnitude and direction of magnetic field. Okay, B vector in magnitude and direction at here because of this current element. And that's very simple. Let the center of the current element is, this is the center, join this center to point P. Okay, and you call it as R vector. And R vector is making an angle theta. This R vector is making an angle theta with current element. Now, magnetic field here is very simple. How? Using Bauer-Source law. You know very well what is the Bauer-Source law. I am writing magnetic field in magnitude, and it is equals to mu naught upon 4 pi. You know what is mu naught over 4 pi? This is constant and having value 10 raised to power minus 7. And this constant it is because the medium. If the medium is vacuum or air, then it's okay, mu naught over 4 pi is taken and its value is 10 raised to power minus 7. But if it is there any other medium, then this constant will change. Now, Bauer-Source law tells us that the field at here, at this point, is ideal, then ideal sine theta divided by r square. This is the Bauer-Source law. The magnetic field at point P because of the small current element. Right? Now then we draw a perpendicular. We draw a perpendicular here. So this is perpendicular. And this is this distance from P to, you say, L is capital R. And from here to here, this length is suppose small l. So lengthwise from here to here it is small r, this length is capital R, this length is small l. And in this right angle triangle, you know what is cos. Again, let I choose this angle also. I call this angle as phi. This angle as this angle. This angle as phi. This angle is 90 degree. Now I'm interested for writing cos phi. Cos phi is base over hypotenuse. So this angle is phi. Then this line is base, mean capital R, upon hypotenuse, mean small r. Or small r becomes R upon cos phi. Now I'm interested also for writing tangent phi. So what is tan phi? You know, tan phi is perpendicular over base. What is perpendicular? Small l. What is base? Capital R. And L becomes R tangent phi. And one thing more. There are three angles in this triangle. 90 degree plus theta plus phi, and sum of the three angles, you know, is equals to 180. And find the value of theta from here. Theta is 90 minus phi. Now what we do? I substitute this theta here, and I'm having the value of L. So if I differentiate it, dl becomes r secant square phi and d phi. I substitute this value of dl here, and I substitute this value of r, you know, at here. So the expression for dB becomes sorry, I'm taking tea, don't mind. dB becomes mu naught upon 4 pi I. Now dl, r secant square phi d phi. You know, instead of sine theta, I'm changing this theta as sine 90 minus phi. 90 minus phi and divided by r square. And instead of r square, I'm writing this r upon cos phi, and this is r square, mean r square cos square phi. Now this 1 over cos square phi is secant square phi, so this cancels with this, right? And sine 90 minus phi, it becomes cos phi. This is cos phi. So expression for small magnetic field becomes dB equals to mu naught upon 4 pi I r cos phi d phi upon r square. This r also cancel with r square and left only one r, right? Now this is a small magnetic field because of this small angle d phi. Now I am interested magnetic field here because of the length x to y. Look, this angle is phi. Now if I consider this end x, then instead of phi I will write this angle phi 1, okay, and now I connect y to this point, and this angle is phi 2. So if I am interested magnetic field for this length x to y, then I will integrate this expression. The limits are, the lower, because this is perpendicular, and the angle which is along the down direction is phi 1 of this end. So I will write here minus. So I will write here minus phi 1 because that's a down angle. Okay, this down angle. Now the upper angle, which is positive angle from this perpendicular, this is phi 2. So phi 1 to phi 2. Now about the integration, the magnetic field B becomes equals to mu naught upon 4 pi I upon capital R cos phi d phi. Limits are minus phi 1 to phi 2. Now what is the integration of cos phi d phi? This is sin phi. So substituting the limits, integral of cos phi d phi is sin phi. So mu naught upon 4 pi I upon R. So this becomes sin phi 2 plus sin phi 1. Here comes plus because of this negative sign. So this is the expression of magnetic field because of the finite conductor carrying current at this point. Now we'll think, if my conductor is very long, if I increase this length, so what will happen? I will join like this. So what happens? This angle will increase. So you go on increasing the length along this side. So what is there? This angle will go on increasing like this, like this. And if this conductor becomes infinite in length along this side, this phi angle goes to then 90 degree because it is increasing. Ultimately it tends to 90 degree when the length becomes infinite. The same explanation is towards this side. You increasing this length, phi to go on increasing, then if it becomes infinite in length, then phi 2 tends to 90 degree. So the case for infinite length, phi 1 tends to 90, phi 2 tends to 90. And what is sin 90 and sin 90? Tell me. Sin 90 is 1. This sin 90 is 1. and field becomes mu naught upon 4 pi I upon r 1 plus 1, 2. So this is the expression for infinite long straight conductor magnetic field at any distance r. I mean to say, if you are having very long conductor, okay, and you are interested here, what is the field? So only the distance which matters, it is this perpendicular distance. Because mu naught over 4 pi, this is constant value. If the medium is constant, then to current which is flowing, let it is constant I. And of course it depends upon I also. But it also depends upon where is your observation point from the infinite long conductor. That is capital R, if this is R. So this is all about the magnetic field. Now this is one question for you. I not explained because the question was what is the magnetic field at here in magnitude and direction, and I derived the value only in magnitude. You tell me, what do you say about the direction of the magnetic field at here? Tell me. Do not? Okay, no problem. I'm giving the hint. You know Poisson law. Mu naught over 4 pi. Okay. I dl vector cross r vector upon r cube. Or you may write it like B is equals to mu naught upon 4 pi I dl vector cross r cap upon r square. Both are equally right formulas. Now think over it. I am giving the hint to you. Think over it. Cross product. You know this vector having direction, this vector having direction, and there is a cross product. And the new vector which comes perpendicular to plane in which these two vectors lies. This is the hint. Now tell me, what is the direction of magnetic field at here? Okay, dl, or you can say current element, it is in this plane, along this direction. And what about r? This is a r vector, it is in this plane. Both are in this plane. Direction will be perpendicular. And perpendicular may be perpendicular, it is outward, or may be perpendicular and inward. Now what do you say about whether it is perpendicular inward or outward? So please write your answer in the comments box. Okay? Thank you.